Welcome everyone. So good morning, good evening, good afternoon, wherever you are. So today we are going to have the QISS seminar. It's going to be hosted by Flaminia Giacomini. As usual, the talk will be approximately 30 minutes, and there will be plenty of time afterwards for questions and to discuss the results, including technical parts. The talk is being recorded. If you have any clarifying questions as the talk is going on, please feel free just to unmute yourself and ask. You don't need to raise your hand. If you have any kind of more conceptual or discussion style questions, then it's better if you can leave those to after the talk. We have plenty of time to discuss those kinds of questions once the talk is finished. And so with that, I'll say I'm very excited to hear this talk, and I'll say, Flaminia, please take it away.
Thank you very much, Matt, for the introduction, and thank you also for the invitation to give this talk. I'm very happy to talk about this work here. So as you can see, it's a very recent piece of work that was done in collaboration with Ling-Chin Chen, and Ling-Chin is here. I saw her. So she's attending the talk, and she was at ETH until a few days ago, and now she is in Vienna. And so the general topic of this talk is the gravitational field associated to a quantum source. And in particular, so there has been a lot of interest recently in studying what we can infer if we prepare a massive object in a quantum superposition state, so in a state that is not a classical state. And then the question that we ask is what we can learn on the nature of gravity from experiments that are performed in this regime. And so I will just show you some new results that we found. And so, but before, let me just, for the people who are not familiar with this field, let me just put this question into a bigger context of like physics and where it is placed in terms of regime. So we are going to talk about quantum and gravity. Quantum because we have a quantum source, gravity because we want to learn something about the gravitational field, but this doesn't fall in the typical regime of quantum gravity. So typically, when we talk about quantum gravity, we talk about the high energy regime, and in particular, we talk about Planck scale effects. And Planck scale effects are typically situated at the Planck scale, which has this value roughly in meters, or 10 to the 19 GeV in terms of energies. So today we are not going to talk about Planck scale physics. We are going to look at the low energy regime, and that is not the typical regime in which quantum gravity research is performed. So that doesn't classify as quantum gravity. And in particular, we are going to talk about a regime in which gravity is in the weak field regime, and also with low energies for quantum particles. So we can meaningfully talk about quantum particles. And the general question, as I already anticipated, is the gravitational field associated to a quantum source and what experiments can tell us about the gravitational field in this case. So this is not a new question. This is a question that has been around at least since 1957. And usually the beginning of this story is placed at this Chapel Hill conference. That was a very interesting conference that happened and gathered many very well-known physicists working on gravity at the time. And the goal was to boost the research in gravitational physics that they felt at the time was being neglected. And among the many questions that they discussed, there was one that is relevant for us today, that is, do we require a quantum description of gravity? And there is a famous thought experiment proposed by Richard Feynman, in which he wanted to argue that out of consistency conditions, then we need to consider a quantum description of gravity when we come up with some thought experiment. And the thought experiment he came up with is schematically reproduced here. So this is a Star-Gerlach apparatus. And this thing here is a 1 centimeter ball. So Feynman was extremely specific in which type of sorts he was considering. So he took a 1 centimeter ball because at the time, torsion balance experiments had been performed, so they knew that the 1 centimeter ball sorts a gravitational field. And now the role of this Star-Gerlach experiment is to prepare this ball in a quantum superposition state of being, say, in position up and in position down. So now Feynman says, since I know that there is a gravitational field that is associated to this ball, then there is an amplitude that the gravitational field is up, in the state up, and an amplitude that the gravitational field is in the state down. So what I can do is to put another particle that this time is a test particle, so a particle that does not source a gravitational field itself, and let it interact gravitationally with the source of the gravitational field. And so he doesn't use the word entanglement, but what will happen if physics knows as we think it works, is that the test particle becomes entangled with the 1 centimeter ball and its gravitational field. So out of this thought experiment, Feynman concludes that if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. And notice that here, Feynman means the term gravitational quantization in not in the full sense of a theory of quantum gravity. The only thing that he means is that the state of the gravitational field can be in a quantum state, so in a quantum superposition state, for instance. And this is the same sense in which we are going to talk about the quantum nature of gravity in the following. So there was a lot of debate that originated from this initial thought experiment in 1957, with many people that contributed to it. And most of them argued in favor of a quantization of the gravitational field. Other people instead argued that the gravitational field should remain classical, and we have very famous models for semi-classical gravity that are around. But recently, so in the past 10 years, maybe, something around that, there was a boost, a new surge of interest in these topics. And the reason is that experiments are, so we're getting close technologically to the situation in which we can realize this experiment in the lab. So just to be clear, at the moment, all experiments that we have are compatible with classical general relativity and quantum particles on it. But now there are two directions in experiments that people are following that try to push the exploration of the experimental exploration to new regimes that are not tested yet. One, here on the left-hand side, is experiments that look at gravity with no quantumness, if you want. So these are torsion balance experiments. Here the goal is to reduce the masses and measure the gravitational coupling between the masses. So basically show that lighter and lighter masses can be treated as sources of gravitational field. And in particular, there is this experiment by Markus Aspelmayer in Vienna that proved that two masses that weigh 90 milligrams can attract each other gravitationally. And if you look here, this is the type of mass that we are talking about. So this is a 1 euro cent coin. So this is something that is very, very small. So on the other side, there are experiments that are trying to show that quantum properties hold at more and more macroscopic regimes. And there are different ways in which you can do that. For instance, here, this is sort of a double slit experiment, very sophisticated one. You try to increase the mass that you put in a quantum superposition and you measure the interference. And here, instead, this is an atom interferometer, so it works at the level of single atoms. And here you try to increase the size of the quantum superposition. And the record is 0.5 meter now. The goal now is to put these two regimes together, and this is, of course, challenging, so we don't have the technology to do it right now, but there are proposals, and experimentalists are trying to push in this direction. And so the goal is to measure the gravitational field that is sourced by an object that is in a quantum superposition state, or in a general quantum state. Now, let me review just very quickly the modern version of Feynman's initial thought experiment, just to give you an idea of what type of things people are thinking, and to just put a little bit more technical details on that, not so much. So in this case, so I'm following these two proposals from 2017. We have two masses, each one sourcing the gravitational field. And initially, they are prepared each in a quantum superposition state of two very well-defined states in position basis. So something that is very sharply localized in x1 and in x2, put in a quantum superposition. And then they interact gravitationally. How do they interact? With the Newton potential. So you just write a normal Schrödinger equation using the Newton potential to calculate the entanglement, the interaction between the masses. Then you let them evolve for some time. And after some time, you can check what the final state is. And if everything works according to the Schrödinger equation with the Newton potential, then the goal is to measure an entangled state. So to measure whether the state has been goes from a product state to an entangled state. Where here you can see that you have a relative phase that is different according to the distance between all the amplitudes of basically the distance between the particles, and the distance is different according to which amplitude I'm considering of the quantum state. And this is the phase that you would calculate with the Newton potential. So now the goal of these experiments is to show that if you have a generation of entanglement, then a classical theory of gravity cannot do it. And so you need to consider a theory of gravity that is not classical. And there are various, so by now there are variations of this proposal, and they consider different types of systems and different initial configurations. But many people have contributed to that. So here, I'm sure I didn't put all the names of the people that have worked on it. But the thing that I would like to stress is that all proposals that we have so far use a coupling that with the Newton potential. And this is a delicate point that has been discussed a lot in the community. And the reason is that there is still no agreement on what we can conclude on the nature of gravity if all the gravitational effects come from the Newton potential. And there are several points of view, which I'm not going to review. I'm just going to tell you what I think about it. So let us see what the limitations of the Newton potential and what instead I think is a safe statement that we can make. So first of all, let me say that measuring entanglement generation by the Newton potential is in any case an extremely important result that we can achieve experimentally. Why? Because as I mentioned before, all current experiments can be explained using classical general relativity and quantum particles on top of it. So you use quantum theory just for the particles and classical GR for the gravitational field. So if we think that there is a more general theory that, that is general relativity, that basically that the Newton potential is embedded in a more general theory, then we know that general relativity and quantum mechanics as separate theories cannot explain the entanglement. And this can also be formulated as a theory-independent no-go theorem, stating basically that if gravity is classical and gravity mediates the interaction, then you cannot have an entanglement generation. But if we want to be really look at the experiment, what this experiment exploits is only the limit of general relativity to the weak field and the non-relativistic limit. So in other words, what this experiment shows is, so the Newton potential is compatible with a specific limit of GR, of general relativity. So even though I think a safe statement that we can make is that general relativity and quantum theory cannot explain the entanglement, we do not know in which direction, which effects are going to come into our description. So we do not know in which direction we should go. In particular, so we cannot prove that the gravitational field is quantum, because the Newton potential by itself is still compatible with a classical description of the weak field limit of general relativity. So what I'm going to talk about today is a new result in which we obtain in the same regime of these experiments a physical effect that goes beyond, that cannot be explained with the Newton potential. So this gives you more information of what the description of the gravitational field should be if you measure this type of effect. Okay, so to do that, let me just start by recalling the solutions of classical Einstein's equations. So these are Einstein's equations, and as we all know, on the left-hand side, we have the gravitational field, so the gravity content of the theory. And on the right-hand side, instead, we have matter. And matter is classical in Einstein's equations. So these equations are only defined with classical matter. Now, if the state of matter is classical, so a classical state, say at a certain point, at a certain time, is ideally a point in phase space. So it is a point, it is something that we can arbitrarily localize in X and P. So what this tells us is that when we reduce general relativity to the limit in which we have the Newton potential, then we are not only considering the weak gravitational field at the non-relativistic limit, but we have also the assumption that there is a classical source. So now, what happens if you put a general quantum source and you want to solve we will not be able to solve this version of the Einstein's equations, but we will see which version of the Einstein's equations we can solve. So if you put a quantum state here, then a quantum state is no longer a point in phase space, but it has a width in X and a width in P. And very famously, this has to obey the Heisenberg uncertainty principle. So we are not in the limit of the Newton potential anymore. And so this means that we have to check what we get for a general quantum source. Now, let me first tell you in which situation we can recover the Newton potential instead, even with a quantum source that is in a quantum state, because this will clarify which assumptions underlie these proposals with the Newton potential and in which way it will be clearer than how to generalize that. And this is contained in this work here. So now let me consider a source of gravity that is in a state that is in a quantum superposition of a localized state in X1 and a localized state in X2. Typically, you will find this written in the literature with these cats that are position eigenstates. But we all know that position eigenstates are not physical. So what we actually mean when we write something like that is a quantum superposition of coherent states, so Gaussian states, for instance. And each one of these coherent states has a width that, compared to our experimental resolution, is negligible. So in other words, if I have some resolution of my measurement device, then the width of this coherent state falls inside the resolution of of my measurement device. So I cannot observe, for all practical purposes, the quantum properties of this quantum state, both in X and in P. And then if I have this assumption, then a good approximation that I can make is to take this each coherent state applied to the T00 tensor, so the 0,0 component of the stress energy tensor. And then on this state, since this is the closest thing to a classical state that we can get in quantum theory, I get the classical energy density. And this would be the energy density that I have in general relativity for a point-like particle. And this is an eigenstate of this operator. Okay. Now, what happens now if I put this quantum stress energy tensor with this type of source into a linearized model of the gravitational field? So the description of gravity that I should consider in this case is called linearized quantum gravity. So what I do is I take the gravitational field, I expand it in a background that is Minkowski plus a perturbation, and then I quantize the perturbation. And then this perturbation is treated as a spin-2 field on a classical background. And now I can linearize also my Einstein's equations, and I find something that makes sense, and it's not controversial. So now I have to find the Hamiltonian of my system, of the source plus gravity. And what I do, I write my Lagrangian, I do my Legendre transformation, and I get to a Hamiltonian of the gravitational field, where now, since gravity is a quantum field, this Hamiltonian will be a function of the gravitational field and its canonically conjugated momentum. And if I want to look for the solution that would correspond to the Newton potential, then I should look at the ground state of this Hamiltonian, because I don't have any particle emission. But now I also have matter. So, and I also know that gravity is a gauge theory. So on top of this Hamiltonian, I also have 4 gauge conditions. And these gauge conditions, as you can see now, I encode the T00 tensor. So all the matter content of the theory is encoded in the gauge conditions. And the other parts, so the other components of the stress energy tensor are negligible because the mass is static. So this first constraint here is called the scalar constraint, and it is basically the Gauss law. And these are there are 3 constraints here, are called the vector constraints, and it gives me the transversality condition of the field, which is basically the same thing we have for electromagnetism. So now it's just a matter of solving these equations and finding the quantum state that corresponds to that. And what we find is that the state of gravity and the source has this form where each one of these states is basically the one that would correspond to a specific position of the source, so to a source localized at xi. And then there is a gravitational field associated to it. What it is? So let us consider first the source-free state. So the source-free state is basically a coherent state. It's a little bit more complicated than that due to the gauge conditions, but you can think of it as again, like a Gaussian state in h and pi, so in the variables of the gravitational field. And then I have to also put the source. So what does the source do? The source modifies this coherent state by some hi0 and pi0, which are functions, and they are the solution of the classical Einstein's equations with a localized source. Because when I apply alpha I and I put it here, then this gives me the classical basically the classical energy density. And so I can just solve this equation with classical Einstein's equations. So this equation, so these states here, the HI, only differ by a classical solution of the Einstein's equations. Okay. But then if we calculate the gravitational interaction between this source and the other particles, and another particle, then we find that we have the Newton interaction. So in this sense, we find the Newton potential again, with a superposition of these localized sources. Now, the question is, can we get more? Can we obtain a situation that is in the same regime, but in which we get something that is not the Newton potential? So what we did was, instead of considering a superposition of these localized and semi-classical Gaussian states, we considered the general quantum source. And so, just to recap, in the case of the superposition of localized Gaussian states, then we have that the width of each one of these Gaussians in X and in P is much smaller than what I can experimentally resolve. And under these assumptions, I was able to write the T00 as basically, when applied to each Gaussian, so this is an eigenstate for the T00, and it gives me as an eigenvalue the classical energy density. But now, for a general quantum source, I do not have these two conditions anymore. So in general, a quantum state will have some width that I can measure with my experimental apparatus in X and in P or in one of them. It's enough that it's in one of them. And if I have now this condition that I can measure this width, that I'm not allowed to make this approximation anymore. But I have to solve this equation in a different way. So for instance, we expanded the state in a convenient basis that for us is the energy basis. The energy basis is motivated because the T00 is the Hamiltonian density. And then we still get a function, a local function in space-time, but this function in principle has nothing to do with the classical energy density. It can be anything, and in general, it depends on the specific experimental implementation that I have. So now let us consider the simplest situation that we can have, in which the source is prepared in the simplest delocalized state, that is wide Gaussian. So it's not important really the shape of this space. The important thing is that it's delocalized so that I can appreciably check the width of the quantum state with my experimental device. I can observe quantum properties. And then we put a test particle just to make it simpler. And initially, we prepare the source and its gravitational field and the test particle in a product state. Then we let them interact with the linearized gravity Hamiltonian, interaction Hamiltonian, where this is the source, this is the particle, and this is the gravitational field. We wait for some time, and then at the end, we again will find a relative phase that is similar to the one that the mechanism is similar to the one that we get in the other proposals for gravitational induced entanglement, but the functional form of this phase is different. In which sense? So you can see here that GT divided by H bar is the same factor that we have in Newton proposals for entanglement. So it's the same coupling in the gravitational field. Now, there is this C to the fourth that looks scary, but remember that in the non-relativistic limit, each one of these energies scales as C squared. So in the end, it cancels out. So this should not be scary for us. And then we have these functions of space. So in this case, I remove the time dependence because everything is static. We don't need anything to move. And And these two are just functions, are general functions. They have nothing to do with the classical energy density. These are just, again, the shape will depend on the specific implementation, but in general, it's different. So now what we did is to check whether we could explain it with some model that kept gravity classical. And so, first of all, this cannot be explained with models that couple classical gravity to quantum matter, so models for semi-classical gravity, like the one that Jonathan Oppenheim and collaborators have been working on. Because these are stochastic models, so they have decoherence and diffusion, while our model is fully unitary. Then, it also cannot be explained with the Schrödinger-Newton equation, that brings, it leads just to a different phase, just a quantitatively different phase. But the most important thing is that this cannot be explained with the Newton potential. And I mentioned that at last because I wanted to comment a little bit more on that. So if we have the Newton potential and we let it act on our state, exactly the state that we had in the previous slide for the source and the particle, then the Newton potential acts in this way, where we have the two masses, the quantum states, and the X cat, where, remember, this is the position eigenstate of the cat. But then, if we take instead our interaction Hamiltonian, and we let it act on the state, here we have the gravitational field because we are treating it as an additional, as a quantum field, then we obtain instead this functional form. And this reduces to the Newton potential only in the limit in which our energy eigenstates reduce to the position eigenstates, well, more precisely to the coherent states that we use in order to calculate the Newton potential for the delocalized source, for the source in a quantum superposition of localized states. And when these functions here reduce to the classical mass density, to the classical energy density, which is exactly the limit that we overcome when we consider our delocalized source. So in general, we cannot do that for this. So overall, it leads to a functionally different expression that cannot be reproduced with the Newton potential. But it reduces to the Newton potential in a well-defined limit. Now, let's look at it a little bit further. So far, we have only considered the effects coming from the interaction Hamiltonian between gravity and matter. But if we consider the full Hamiltonian, then we have the Hamiltonian for the source, the Hamiltonian for the probe particle, the Hamiltonian of the free gravitational field, and the interaction Hamiltonian between gravity and matter. So now, gravity is treated as a quantum field. So it has quantum operators that do not commute, well, commute canonically. And here I just added this alpha as a bookkeeping device to remember where I have one commutator between the gravitational field and the momentum. And then we want to set it to 1 at the end. But the important thing is that the commutator between the free gravity Hamiltonian and the interaction Hamiltonian does not commute even when it's applied to the physical state of the theory. So this means that we have some correction terms to the relative phase that we saw in the previous slide, that, as you can see here, there is a part, so the coupling in gravity is the same order as the Newton potential. It is higher order in time, and then it has some terms. So this one depends on one commutator between gravity and its canonically conjugated momentum. This one here depends on 2 commutators, and the rest of the expression only depends on the operators of the probe particle here. And in particular, I can increase this term here if I have probe particle states that are very different in energies. So that's one way to to increase at least this. So this is most likely more challenging to measure in the laboratory. So first of all, it is higher order in time, and given a certain time of the experiment, this can it can be smaller for small times. Well, it is smaller for small times, but if it is there in principle, and if one gets to measure that, then we have a stronger indication that gravity is a quantum field, because this is a term that would not arise in a classical theory of gravity, even when gravity is a field theory. So to conclude, I think that the best statement that we can do if we measure entanglement via the Newton potential is that this effect is not compatible with general relativity and quantum theory taken as separate theories. But what I wanted to convey in this talk is that in the same regime for these experiments, we can do better than that. So we can obtain more information on quantum features of gravity. And in particular, we identified two effects that are beyond the Newton potential, but are the same order in decoupling. When we consider a static quantum source of gravity that is, however, in a delocalized state, so that does not fall into the localized semi-classical state that is put in a superposition. That is the one that is usually considered. So the first one is a dynamical phase that arises as a relative phase in an interferometer that cannot be reproduced with the Newton potential, nor with at least one non-classical model of gravity. And the second one is an effect of the quantum commutator of the gravitational field and its canonically conjugated momentum that appears as a correction in the phase when we have a source of gravity interacting with a test particle. And this would be a test of the role of gravity as a quantum mediator. So these are effects that are not relativistic and do not depend on graviton emission. And I believe that studying this type of effects is crucial to plan a new generation of experiments that test quantum aspects of gravity in a broader sense than what has been discussed so far. And now the open questions that we have are just how to concretely implement this experiment and to put numerical estimates. And with this, I would like to thank you for your attention.
Great, thank you very much for that, Flaminia. Okay, so it looks like we have a lot of questions in the chat. So actually, yes, 1 second. Good, okay. So I believe we have, I pronounced it correctly, a question from Tae Hun Lee.
And first, actually, you are working on the gravity, but we can also think about the electrodynamics, for example, Coulomb potential. But I'm trying to ask what's the significant difference between the electrodynamics and gravity? I guess actually you said the interaction, gravitational interaction, it doesn't commute with the Hamiltonian of gravitational field. But I don't know about actually electrodynamics, whether this kind of condition actually also hold. But I feel like maybe electrodynamics, when you do same actually experiment, it can be actually simpler than actually gravity case. So can you explain?
Yeah, no, I agree with this. Yes, there is a completely analogous effect for electromagnetism. And actually that is interesting to look at because this could even be feasible to measure in an experiment. So I just didn't discuss it because the gravity effect is harder actually also to calculate and to derive. But for electromagnetism, it would work in the same way. just like differences because electromagnetism is spin 1 and gravity is spin 2. But apart from that.
Okay, thank you very much.
Great. So we have a question from the big group at Western.
Karen, can you hear me?
Yes.
Yeah, Flaminia, this is Carla. This is very nice, and I find this wonderful. I've just a sorry, a question. I'm trying to get a sense, a physical intuition about this extra effect. I was wondering if the following is. I mean, the mathematics holds; it's clear. I'm just trying to make a picture in my head. I was wondering if the following makes sense or is just oversimplifying the story. The particle, the S particle, is not just spread in position in its generic quantum state. It's also spread in momentum. And the two things are obviously, in some sense, correlated to one another. And that's what brings us outside the easy thing of saying, well, it's here and here, the Newtonian potential one place and Newtonian potential the other place. Is that a wrong way of thinking, or it's a could hold?
No, I think it's, you can think of it in this way. So another way you can say is, so you are in the limit when you can make the approximation for the classical energy density, when you are able to neglect the commutator between x and p when it acts on the quantum state. And in this case, you would not be able to neglect it. So it's really the structure of quantum mechanics that prevents you from doing the simplifying approximation. Okay. I don't know if that answers your question.
Yeah, I think it's consistent. It's yeah, I mean, you keep thinking of the math. Yeah, but I think it holds. I wonder one thing you have not done is to write explicitly how this E function comes out of the state. So I suppose that's where I should look at
Yes, that's something that, yeah, exactly. So,
but you have it, right? You have it explicitly in your paper. You know how to write it explicitly.
Yes. So we know how it comes out. We do not. So what we have to do is, for a specific implementation of the experiment, how to do it, basically, like which specific form we have to put given an explicit implementation. But that's the Hamiltonian density of the field. So
yeah. Thank you. This is great. Thank you.
Thanks.
Okay, so we actually have a couple of questions in the chat. So we have one from Bruna Sado. I'm happy to read it out, but also if Bruna Sado is there and they want to ask the question themselves, then I'll give them a chance to unmute themselves and just go ahead.
Oh, okay. Hello. Congrats. I just wondering, like if there are any estimates for or calculations did specifically for the scale of the mass that would be needed in an experiment so that the phase could be really detected in a considerable way, Are there any estimates? So
this is the part that you're actually missing. So I would expect it not to depend only on the, I would expect that there are different relevant scales that come into place in order to estimate whether we can measure this effect in the same way in which there are different scales that come in the usual like Newton potential tests. Right. So for instance, there it's the mass, the distance between the two masses, and the delocalization of each particle. And so something like that could also enter here. But this is a part that we haven't looked at yet. Okay. Because it required already like a lot of effort to get to this point, and then this is
yeah, understood. Thank you very much.
Thanks.
Okay, great. We actually have before the other hands that are raised, there's one more question in the chat. So again, I hope I'm pronouncing it correctly. Gorab, if you're there and you would like to unmute and ask the question, then go ahead. Otherwise, I can ask it. Okay, so they won't be able to talk. So I'll read out the question. So thank you for the talk. I'm wondering if, assuming that space-time is non-commutative, has the same effect as considering commutator gravitational field operators. Does it make sense to take these approaches to be dual to each other? So you can also see this question in the chat if you want to reread it.
Okay, so I'm not sure to which type of non-commutativity of spacetime you're referring to. If you're referring to like deformed commutation relations, for instance, then this is different because like that introduces like a minimal scale at the Planck length, and instead here we have just a normal quantum field. However, in a sense, this is making spacetime quantum if you also consider the perturbation of the gravitational field to be a part of spacetime. So in this sense, yes, it is some sort of but in a different way to what you would call non-commutative spacetime. So it's like there is this is distinguished.
Okay, great. So we have a question next from Philip.
Thank you very much, Flaminia. Can you hear me okay?
Yeah.
No, I appreciated your talk. At the beginning, you mentioned that classical gravity plus quantum mechanics cannot generate entanglement. And maybe this is a simple question, but I was thinking about the hydrogen atom, and with a classical background potential, you can generate entanglement between nuclei and electrons in non-relativistic quantum mechanics. So can you help me understand why is it that a classical gravity field as a background potential in a non-relativistic quantum theory cannot produce entanglement when electromagnetically it can?
Sorry, can you specify your question a bit more? So in which sense in the hydrogen atom you can have like just a classical potential? And because usually, I mean, this happens also with the harmonic oscillator if you want. So you write a harmonic oscillator and you have a classical like spring if you want.
Yes.
But then this is usually not treated as a degree of freedom of its own. So if you actually want to treat so usually you write it as a direct coupling between the two masses that you're entangling. But if you take really seriously the fact that the spring is a spring, and then you associate some physical degrees of freedom to the spring, and you only let, say, particle A interact with the spring locally and particle B interact with the spring locally, then this will not generate entanglement unless you have like a quantum model for the spring. I
see. Okay. Then I think that answers my question. It's an effective entanglement. I mean, but this is exactly how they treat entanglement in real matter. The effective potential is a classical background field.
Yes, exactly.
So you can, okay. All right. Thank you.
Okay, great. So next we have a question from Pablo.
Hello, Flaminia. Can you hear me?
Yes. Hi.
Okay. Hello. So my question is this. When you have a Gaussian wave packet well localized in position and momentum, then I understand that you can deduce the gravity effect. If you have a superposition of them, then I understand as well. But then if you have an arbitrary wave packet, what tells you what the gravitational potential will be? I thought we had no theory for that. No, unless maybe you can decompose your arbitrary wave packet as a sum of Gaussian states, then I would understand. But if you like, I'm looking for the principles that you have there to interpolate from the classical to the quantum wave packet source.
No, okay. So, no, that's a good question. So Okay, so the theory of coupling a quantum gravitational field in the linearized regime to quantum matter is there. It's fine. Then it can be hard to solve it. So now, as long as you have a static mass and the particle in a general quantum state, in an arbitrary quantum state, you can solve it in the way Ling-Chin and I did in this paper. So in a way, you can think of it as really solving the Hamiltonian of gravity and matter for a static source for the general quantum state. Now, there are additional complications, though, if you have a general quantum source of gravity. For instance, because at that point, because we exploited the fact that there is an energy eigenbasis for the T00. And for a general quantum state of the source that, for instance, moves as some dynamics that you cannot neglect, then, for instance, the different operators do not commute. So the T mu nu does not commute with itself. It's called the Schwinger term. And then you cannot do this simplification anymore. For us, it commutes, so we could expand it. But then in a more complicated case, you could not do this expansion anymore, and you would have to find another technique. But in principle, the theory is there. And then I think I missed the second part of your question.
No, I guess so. Mainly, you're answering that there is already a sort of quantum linearized version of
yes,
of gravity that you use there,
yes,
and that sort of knows how to handle non-Gaussian states.
Yes, yes, this is what I wanted to mention, that we also checked what happens if we expand a general Gaussian state as a superposition of localized Gaussians. And that is functionally different to what we obtain if we just do the quantum source straight ahead. Because what we obtain when we localize the Gaussians is again a superposition of Newton potentials. And instead, when we do the quantum state as a whole, then we do not make this approximation, and then we get the additional effect. So it's actually really important not to go through the superposition of localized Gaussians in order to solve the general quantum state.
Okay, thank you. Thanks.
Thanks.
Okay, now Weston.
It's Carl again. It's more of a comment, and maybe Flaminia, you can comment on what I'm saying. I was listening the previous question from the chat by Garab, in which he asked whether something similar could be obtained in non-commutative geometry. That sounds very interesting, because it made me thinking. In non-commutative geometry, the idea that quantum gravity has to do with a small structural space-time. At a very small scale, something happens, and this has an effect, I don't know, in singularities, black holes, and there are other ways of thinking quantum gravity that think at quantum gravity in that way. All this phenomenology you're talking about, it's pointing to the fact that quantum properties of a gravitational field might include effects which have nothing to do with that. It's profoundly away from that. That regards large space-time regions compared to the Planck scale and low frequency modes and so on. So quantum mechanics applies to large wavelengths, so to say, to big things. So in a sense, these effects you're pointing out, interesting not only because they go beyond Newtonian thing, but also because they make the point that we might expect from quantum gravity something which is nothing to do with the short-scale structural space-time.
Yeah, I agree with this comment. Yes, fully agree.
Okay, Nick.
Hi, Flaminia. Thanks for that. That's very, I find that very, very interesting. That's very cool. I I mean, I think you've answered this question in a couple of ways already, but there was I just wanted to make sure I'm getting things sort of clear here. And it has to do with the calculation in the first place at the dynamical phase. And when you say sort of no known classical model of gravity, because there was a stage where you basically are writing down, you're sort of you're finding the eigenstates and values for the T00 component. And so one of the things you might think you're going to do there is sort of take the expectation value of the stress energy tensor, and that this would be a semi-classical gravity calculation, but that's not what's happening, right? It's all quantum. I just wanted to make sure I was getting that right.
Yes.
Okay.
Yes. If you
Yeah,
take
very
the
nice.
expectation value of the stress energy tensor, you get something like the Schrödinger-Newton equation, and that leads to different predictions. So
yeah. Okay, great. Thank you. Thank you.
Okay, Ali.
Thank you. Thank you, Flaminia, for the nice talk. As I maybe mentioned recently, I think I've done something which I think is very similar. Can you please open the slide again where you have the phase term, the new phase term for the general state?
This one?
Yes. Okay. So is this, so my maybe first question is this any different from if I have the BMV experiment and instead of having, let's call one of the two particles the source and the other the probe, it doesn't matter. So one of the two particles in the BMV experiment, if I have it instead of a superposition of 2 paths, I have a superposition of 3 paths, or then 4 paths, or actually I have a superposition of a number of paths, and each with a different probability. This is what you are doing here, right?
No, not exactly, because if you did something like that, then you would fall into what I was saying before, answering before to Pablo's question, that you take the approximation of the superposition of localized Gaussians, and this leads to a different effect than if you just take the gravitational field associated to a general quantum source and you just solve it straight away. So this is more in that spirit. But it's not just a BMV with a lot of paths. It's just different.
I see. I think the difference, the reason it is different for you is that you take the source to be in a superposition of energies rather than superposition of locations. Is it not the reason?
No, it's really the fact that the source is delocalized and that it doesn't fall into the approximation that you do for the BMV.
Okay. I'll need to think about that a little more. Thank you.
Welcome.
Okay, Deepak.
Yeah, hi, Flaminia. I guess my question is perhaps a little bit more elementary than most, which is that why do we believe that that position is a good quantum observable in terms of which you can define states and entangle them? Because I mean, as far as I know, we don't really have any good operators which correspond to, let's say, the position of something in loop quantum gravity, let's say, or in other quantum gravity theories. So,
yes.
Yeah.
So you are talking now about the usual proposals for like gravitational induced entanglement through the Newton potential, because we didn't use position basis for our calculation. But okay, in that case, so it is true that in general, in special relativistic quantum mechanics, quantum field theory, you do not have a good position operator, but you can think of this regime as an analogous regime to what you would have in quantum optics experiments, where you are still allowed to treat the matter in the non-relativistic regime. So this is just Galilean quantum mechanics. And then you have a position operator. And so you can make sense of the position also operational. You can measure position, you can do whatever you want. And then the gravitational field is treated as a field. And that's actually parallels very, very closely what happens in quantum optics, just with the electromagnetic field instead of gravity. But that's a typical regime that experiments address all the time.
No, I mean, the position is very different from the electromagnetic field, right? I mean, how can you compare the two?
Position is for matter. So you only need to talk about position for the matter source, and the matter source is not relativistic. So you can do that. And for the gravitational or electromagnetic field, you never talk about position.
Okay. I mean, I'm not convinced, but okay. I'll leave it at that.
Okay, Daniel.
We cannot hear you.
Daniel, you're currently muted.
Oh, sorry. Thank you, Flaminia, for your talk. I was looking at this relative phase in precisely this transparency, and I was wondering at what point, or if at some point, did you consider that the superposition involved states that had no overlap, or if you didn't, then we could do this with any state of, let's say, a particle in an atom or something like that, and divide the particular state into the superposition of two states in an arbitrary manner. And if that's the case, then it seems to me that this phase would have serious problems at the points in which you would have overlaps, right? You take any state, and you divide it into two states into the sum of two states in an arbitrary way. I can do that in an infinite number of ways. Even a Gaussian I can divide in that manner. And then if I try to compute this phase at the points in which both ES of X and EP would have equals, would have support, the denominator you have there, diverges, and this expression becomes problematic. So was there a point in which you require in your approximations that the separation of your state was done in such a way that there was no overlap between the two components?
So in position basis, it can be anything, but then you have an energy eigenbasis. So in that case, you have just a basis.
Well, but here it says ES of X and EP of Y, right?
Yeah, but that's the eigenvalue. Yeah. And this is because it's a field, it's a quantum field. So this is not, so this is the eigenvalue of the field applied to the state.
Right, but why couldn't there be points X equal to Y in your setting?
Okay, sorry, you mean because you could okay, but that's the same thing that you would do with the Newton potential. So
Right. So
okay, it's the same type of okay, now I get the question. So in this case, so this is okay, this is the source, this is the probe particle, and they are separated, so they are not together.
Okay,
So,
but what prevents me from considering them in a case in which they overlap? What step in your calculation prevented me from they having an overlap?
Well, we didn't put it explicitly, but I would guess that in that case, we would need a regularization of the phase.
And that would that regularization come out of any type of known previous regularization of the energy momentum tensor or something like that?
Yeah, the usual ones, I would guess. Yes.
The usual ones.
The usual ones that prevent you from, like, for instance, considering the Newton potential when the two particles collide. So it's the same type of divergency. And also, actually, you have to see how this scale, because it could be that this go to zero more quickly than how quickly this go to infinity. So,
but it seems that that's under my control, right? I can choose the source and the probe arbitrarily, and I can control them and put them.
Yeah, but
whatever condition in which they do not.
Yes, but they have to be physical conditions, of course.
Right.
So you cannot put them just in any condition.
Right. For instance, hydrogen atom, the wave function of the ground state of an hydrogen atom, the electron wave function overlaps with the proton wave function. So we should already see some effect in the hydrogen atom. No?
So I don't know exactly which effect you're referring to, like divergences.
Yeah. Or the reminder. Even if I do the renormalization, there would be some reminder. That could be very large because there is a denominator that is becoming very small.
Yes, but so this is also so this is not the support of the wave function. So this is also important. This is just the energy density, and it does not coincide with the support of the wave function. So it depends on the specific experimental implementation, and all these implementations are done by localizing the particle in a potential well, for instance. Right. And so you would have to take this into account when you put a specific.
Right, but I imagine that if I have a symmetric situation, that point X would correspond to the precise center, right? And if I think of an hydrogen atom in the ground state, both the wave function of the proton and the wave function of the electron are centered at the same point.
But this would not be the case in this situation. You will not center them at the same point because otherwise you cannot.
No, I'm not asking doing a new experiment. I'm saying consider an hydrogen atom as a realization of your experiment.
So the comments from Weston, we can't hear you in the mic so well. Yeah.
Oh, sorry, I left, but maybe if I just jump in, why should that diverge? In 3D, this is a 1 over r. You go to polar coordinates as r square upstairs. This constant does not diverge.
Yeah, this is also what I was trying to say when I say that this can go to 0 more quickly than this one diverges.
Okay. It's not the E that goes to 0, it's the measure that you're saying that's going to 0.
If you want, yes, if you want. This is a convergent integral.
Okay, but it would provide, a contribution, and you would see, for instance, in the difference between an hydrogen atom with electron and a muonic atom.
You can measure the relative phase.
Yep.
The difficulty is just setting up the thing and measuring the relative.
Yeah, I mean, people are already doing those things, constructing atoms that are, muonic atom and an electronic atom, and they should be different because the electron and the muon have different energies. And what I'm saying,
I mean, one would have to put numbers in and see like
yeah,
what
of
the
course.
estimate of the size is, and like so it's I cannot give you a full answer now because I do not have all the full information to tell you if they should already see
Right,
this.
but the point is that the point that I wanted to know if there was some part of your argument in which an overlap was forbidden, and you said somehow, if I understand, no such requirement is made in your calculation.
No.
Okay, thank you.
Welcome.
Okay, Ali.
Thank you. So Flaminia, I was thinking about this. I think I get exactly this phase simply by writing. Remember the state in the BMV experiment, instead of L plus R for one of the particles, some x and the integral over x, some ket x and the integral over x, and then for the probe I have a ket y and the integral over y with probabilities, and then I have exponential of minus I Hamiltonian t, and with the Newton potential, but turned into an operator. So I have the x is an operator, the y is an operator, and you get exactly this. A bit more general because you have you can control the probability distribution,
but this is not the Newton potential. This is really not the functional form of the Newton potential. This is what I was stressing.
Yeah. So can you explain that point, because I think I miss it.
So you only get the Newton potential if you have this condition here. Otherwise, this is a functionally different form to the Newton potential. So it is really like different, like quantitatively different to the Newton potential.
You mean that E is a different
as a different function? It's not this function. So the Newton potential, you only get it if E has this shape, but for us E is general.
So for you, E is M multiplied by some probability distribution, right?
Not even a probability distribution. It can be any function. Like it is not
and what determines that?
It is not an amplitude, a probability amplitude. It's something else. It's a function.
What kind of function? Like function of what?
It depends on the specific implementation, but it is not anything that corresponds to a classical probability distribution. That is what you're telling me that you have.
Right. Yeah, okay. I was hoping for just a clarification on what instead it is, but I can also read the paper, so to save you the if it's complicated to explain it in a sentence.
Yeah, but, and I think we should keep discussing it offline in any case.
Sure.
Okay, Hugo.
Thank you.
If you are able to ask the question, otherwise I can just ask it from the chat. Let's see. Okay, I don't see anything from Hugo, so I'll start reading. Okay, so thanks, Flaminia, for the nice talk. I'm just thinking, if you are asked to bet for a suggestion of an experiment, what kind of quantum source and what kind of gravitational system would you propose to test the entanglement?
So I'm not an experimentalist. What I can say is that I'm personally in contact with Markus Aspelmayer for this type of effects, and he has levitated quantum systems. But I think, an experimentalist is better suited to answering this question than me.
Right. Okay. And then we had another question from Gaurav, which said, perhaps there are analogous condensed matter systems realizable in the lab, ? These seem to be the general trend these days. And maybe this was a response to the previous
Yes, no, I would guess that there are analogous systems that you can do with like analog gravity or things like that, so where you can simulate this effect. Yes, that's correct.
And we have, I think, another question from Daniel.
No. Sorry.
Just a raised hand. Okay, cool.
Sorry.
Okay, well, I think we have. We have another question in the chat. Okay, so this is from Alessandro. Thanks for the very interesting talk. It's my understanding that most of the tabletop experiments that we are thinking of for quantum gravity start from gravity and non-locality. Do you know of any tabletop experiment investigating the possible relation between gravity and undefined causality? I'm in a very noisy environment and I won't be able to talk, sorry.
So the only it's not a proposal for a tabletop experiment, but there is the gravitational quantum switch that addresses the relation between masses in a quantum superposition and indefinite causality. But that is not a proposal for an experiment, and I would guess that the effects for that are just too small. So we are already struggling to generate entanglement between two quantum sources. So the testing indefinite causal relations with gravity is like even harder than doing the first basic experiment that we can hope to do. So yeah.
Okay, I think it looks like we are out of questions and we've had a lot, so that's great. So yeah, if there are no other questions, then at this point I'll say thanks very much for the really nice talk, Flaminia, and yeah, well, thank you.
Thanks.
Great.